We just discussed Young's double slit experiment and found an equation that relates the angle of diffraction to the wavelength of light. So we're going to focus more on that wavelength and talk about the diffraction of the different wavelengths of the visible spectrum. Now, as a reminder, here are all of the different wavelengths of visible light. You can go from 400 nanometers in the violet region all the way through 750 nanometers in the dark red visible region. So as you go beyond less than 400 nanometers, you get into the ultraviolet. Anything longer than 750, you get into infrared, which aren't visible to the human eye, but they are there all the same, and they actually follow the same principles. So whenever you see the diffraction patterns that you will in the next couple of slides, just remember that ultraviolet and infrared also diffract similarly in those pictures. All right. So the amount of diffraction that happens, in other words, the wavelength of diffraction, depends on the wavelength of light. But what's interesting is that the index of refraction also depends on the wavelength. So what we see here is a series of different materials, glass and quartz are what we're looking at. And we're looking at their index of refraction, which is the y-axis of this graph. And the x-axis would be the wavelength of light. We'll take silicate crown glass because that's pretty close to 1.5. For red light, silicate crown glass has an index of refraction of 1.5. But as you start getting into the yellow range, notice that it's up a little bit higher. Green at 500 nanometers, it's a little bit higher still. By the time you get to violet, it's around 1.52. Yes, that's around 1.52. So the index of refraction also depends on the wavelength of light. Now we won't dwell too much on this. We don't have any equations to deal with at this time on how to find the index of refraction based on the wavelength of light. You will be given that information. It's just an important point to remember is that the index of refraction does depend on the wavelength. Okay, so this variation in the index of refraction, along with the dispersion because of diffraction itself, explains why when you have light and you shine it through a prism, the light actually splits apart. They diffract at different angles because of the different indices of refraction, and also because of the the diffraction angle depending on the wavelength as well. Again, remember that you also have infrared here and ultraviolet down here. So you get white light shining through a prism, and you see that the white light is just a combination of all of the colors: red, orange, yellow, green, blue, and violet. And now we're ready to talk about one of my favorite things, which is what makes a rainbow a rainbow. Well, first of all, here's your raindrop right here. Sunlight comes in on the top, and it causes the light to refract so that the red light, the violet light is going to refract a little bit more. The violet light is going to refract a little bit more, and the red light a little bit less. And then they both bounce off of the back side of the raindrop and move towards the front side of the raindrop. Because of the reflection, the colors actually cross each other and are reversed. So violet comes out on top and red light comes out on bottom. But then you look at a rainbow, you say, no, that's not right. The red is on the outside. Well, rightly so. But the upper raindrops, because they're higher, the violet rays just pass straight over your head, while the lower red rays are the ones that reach your eyes. Whereas droplets that are further down, because violet light is refracting more, violet light comes out on top, you see that violet light there, whereas the red light refracts less and is going down beneath your eye. So the higher raindrops you see as if they were red, the lower raindrops as if they were violet, which is why you get the rainbow as you see here in this picture.